Hey guys, it's Saturday morning and
Hi.
I'm trying to finish up this problem set. So I have my son Whit with me and he wanted to say hello. And he's been a real trooper sitting through the past 5 or 6 of these. So he helped me erase the board and now he's going to help me solve this by observing from right over there. Okay, so we're doing problem M on OEH 5723 homework 2. So problem M, we've got mercury with a molecular weight of 200.6 grams per mole, and we are trying to determine what the concentration would be if we had a saturated vapor, and we know that the vapor pressure of mercury is 0.0012 torr at 20 C. So the pressure of the vapor equals 0.0012 torr at 20 C. Okay, so this is not 25 C, so our molar volume will be different if we have to use it, which we will. So what we should first think is this is just like the last problem where we're going to take the vapor pressure, we're going to divide it by the atmospheric pressure multiplied by 1,000,000. That'll be our ppms. Then we'll convert to milligrams per cubic meter using molecular weight and molar volume. Then we will multiply by 1,000 to go from milligrams per cubic meter to micrograms. So let's do it. We have our ppm. Our ppms of mercury are going to be equal to our vapor pressure divided by, our pressure of vapor divided by pressure of atmosphere times 1,000,000. Right? So this equals 0.0012 torr divided by 760 torr times 10 to the 6, which is 1,000,000. Since our units will cancel, we know that we're on the right track for doing ppm. So 0.0012 times and divided by 760 times 1,000,000. Alright, so you should get 1.6 ppm. Alright, not a whole lot, right? But it's still more than I would have expected if I hadn't worked this problem already. Now we need to go from ppm to milligrams per cubic meter. So C ppm multiplied by the molecular weight, so 200.6. Sorry, I had a 6 on the brain. 200.6 grams per mole divided by molar volume. So in this case, it's not 24.45. So I'm being a little tricky. You're going to have to calculate it. So remember, we have PV equals nRT. Solve for V. Your P cancels. So V equals nRT. So molar volume means we're assuming 1 mole. We have our gas constant of 0.8623. 02. And that is going to be liters, atmospheres per mole Kelvin. And then we multiply it by temperature in Kelvin. So it's not 298, it's going to be 293. And if you wanted, you could do 293.15. And then that'll be divided by our pressure in atmospheres, and this is assuming we're at ground level, still sea level, so it's just 1 atmosphere. Alright, so atmospheres cancel, moles cancel because that's in the denominator, kelvins cancel because that was in kelvins. So we're left with liters, right? So this is what we've done previously. It shouldn't be new. So the molar volume at 20 C is going to be slightly different. So I'll type this out real quick. 0.0 0.8206. Keep it down over there, Whit. 0.08602 times 293 divided, that's it. So 25, no, I'm not doing something right. Now what's my gas? Maybe I've got the gas constant wrong. Right, I have my gas constant wrong, so I had it written right the first time. Okay. It's 0.08206. 0.08206. Now, if this was class, I would have expected you guys to correct me sooner, but anyhow. So, we all make mistakes. We just got to correct them. Notice when they don't seem right. So, I noticed that didn't seem right because at a lower temperature, I know that my molar volume should be smaller than 24.45, and my calculation came out to 25. So, this comes out to 24.04 liters, right? So that's my molar volume, 24.04 liters per mole. All right, my per moles cancel. And in this case, remember, this automatically has us adjusted by a factor of 1,000,000 to get out of the ppms and into milligrams per cubic meter. And so what was this concentration? It was 1.6. So we can just do 1.6 times 200.6 divided by 24.04, and we get 13.4 milligrams per cubic meter. Okay, so that's in milligrams though, so we need to multiply by 1,000 micrograms per 1 milligram, and so now we have 13.4 thousand, or 13,400, 1,300 micrograms per cubic meter. Okay, whoa. Earthquake. No, I bumped the wall. I bumped the desk. Alright, so that is the answer to our question. So the other thing that we could consider is how does this relate to the exposure level? So if you have a mercury thermometer that gets broken in a classroom and it's just allowed to stay in that classroom, it seems like, oh, well, that mercury, it doesn't evaporate very fast. It's really not going to be a health hazard. Well, if it sits there over the weekend and the air conditioner's turned off, then we have our exposure, and our saturation limit is going to be 13,400. And if I look up on NIOSH, they say that it's immediately dangerous to life and health at 10,000 micrograms per cubic meter. So we're in the immediately dangerous to life and health category right here. So that's some pretty serious mojo. Alright, that was our homework set. That took me a lot longer than I thought it would, so maybe next time I will make it a 20 or 30 minute deal and I'll just run through them all on the big board. I don't know. Y'all let me know how you liked having these explained to you, and we'll go from there.